This is GATE 2016 set 1 ECE question number 24. It says concentric spherical cells of radii 2 meter, 4 meter, 8 meter carry uniform surface charge densities of 20 nanocoulomb per meter square. So it is surface charge density and minus 4 nanocoulomb per meter square, and the third one they have not specified, it is rho s. Now the value of rho s in nanocoulomb per meter square required to ensure the electric flux density is 0, that is the net electric flux density should be 0 outside at a radius of 10 meter is. So it is outside a spherical shell configuration where there are 3 cells, and the value of the third surface charge density of the third spherical cell is being asked. So in order to solve this question we need to know some useful data that will help us in order to find out the solution. Now Gauss's law states that flux leaving any closed surface is equal to the charge enclosed by that surface. So for example, this is a surface. Now the electric flux at this point, let it be phi. This flux is equal to the net charge enclosed by that surface. So imagine an imaginary surface and is equal to the net charge enclosed by the surface. This be psi electric flux, which is given by dds, where d is the electric field density vector, is equal to q net. So if it is some q net, or even in distribution, so all these net charge enclosed within this closed surface, that will give us a value of net electric flux for this surface. This is net flux enclosed, so leaving the surface, so net flux leaving the surface is net charge enclosed by the surface. So now in the question they are given 3 spheres, 1, 2, 3. Now note, these are shells. Shells means they are hollow spheres only having surface, no volume, that is no solid content inside them. Now for example, this is some charge there. Now as per the question given, 20 nanocoulomb per meter square, so per meter square there is 20 nanocoulomb when positive charge, then minus 4, so there is negative charge, minus 4, so 20 nanocoulomb per meter square shell 1, and for shell 2 it is minus 4 and also nanocoulomb per meter square, right? Nanocoulomb per meter square, and for surface 3 it is rho s. So this is the configuration. Now at a point 10 meter they are asking outside, 10 meter, and the 2, 4 and 8, so this is 2 meter, this is 4 meter, this is 8 meter. Coming to the solution, at a point at this location, this is the sphere and this is the configuration. Now somewhere at this point, imagine outside the configuration, the d vector has to be 0. By applying Gauss law, integral d dot ds must be equal to net charge enclosed. Now this should be 0 at this point, so net charge enclosed should be 0. It implies net Q equal to 0. Now Q for 2 meter plus Q enclosed for 2 meter plus Q enclosed for 4 meter sphere plus Q enclosed for 8 meter sphere must be equal to 0. Now how you find charge enclosed for this? Now the data is given that for sphere 1 2 nanocoulomb per meter, 20 nanocoulomb per meter square, 20 nanocoulomb into the area of a sphere is 4 pi r square. Surface area is surface area into surface charge density gives you total charge for that surface enclosed for the surface plus minus 4 nanocoulomb into 4 pi r square, where r, what is r? R is 2. So for this sphere, and for this sphere r is 4 pi r square. For 4 meter it is coming plus rho s, which is need to be determined, into 4 pi r. What is r for this sphere? R is 8 into 8. So this should be 0. Now this is coming out to be 320 pi nanocoulomb. This is coming out to be minus 256 pi nanocoulomb, and this is coming out to be 256 rho s pi nanocoulomb. So nano can be cancelled, and we can write 320 pi minus 256 pi plus 256 rho s pi equal to 0, implies rho s equal to minus 0.25. So since we already reduced in nanocoulomb, rho s is already coming in nanocoulomb, so rho s equal to minus 0.25 nanocoulomb per meter square. This should be the value of the surface charge density of third hollow shell, such that the net electric field density at the outside point to this configuration coming out to be 0. The answer is minus 0.25 nanocoulomb per meter square. Thank you.